I'll soon put up the key for exam 1. Scores are all over the place. Some did quite well. Some did not. But please bear in mind, as I've already told you, this stuff is challenging and difficult. But if you're going to learn chemistry, you must be shown what chemistry is about, which we do in this gathering. So if you did not fare well on exam 1, there's all kinds of remaining opportunity available to boost up your score, your point achievement, and your grade. One more reason why I built all sorts of earnable extra credit into these quizzes and exams. I know this stuff is tough. I'm sympathetic with you. I want to give you the chance to get it. But you have to do your part. From the questions which fell into the most commonly missed category on exam 1, I conclude that for those who did not do well, the most commonly neglected consideration, which you simply and flatly cannot neglect or overlook or foul up, is this. You know what this is. If you cannot write for a system like a solution, a principal species inventory, and as necessary determine moles of each system component, principal system component, after that you can't do anything with the problem. Did you notice on exam 1 how many times I asked you to consider this solution treated with this stuff? By appropriate treatment of this solution, I forget the molarity, maybe it was 1, doesn't matter. By appropriate treatment of this solution, a given volume thereof, which I specified in each case, because if I don't tell you the volume, you can't do this part. With appropriate quantities of this, you can leave this solution as fairly acidic, because you only had a little bit of this, which means you'll still have hydrogen sulfate ion at high concentration. Or you can add enough of this to convert an appreciable quantity of this into sulfate ion, which gives you a hydrogen sulfate ion buffer. Or you can add enough of this to murder all of this. Now the principal species inventory is ammonium ion and ammonium ion and sulfate ion. And Ka ammonium ion is a hell of a lot bigger than Kb sulfate ion. So now you in essence have a solution of ammonium ion. An acidic solution, but not nearly as acidic as this solution, because hydrogen sulfate ion is a much stronger acid than ammonium ion. Then, if you add more of this, you can turn it into an ammonium ion ammonia buffer. Then, if you add more of this, you can turn this into essentially an ammonia solution. Get more basic, more basic, more basic. Then, if you add even more of this, you can turn it into a solution in which the hydroxide ion molarity supplied by adding an abundance of this dictates solution pH. Same mix all the time, except that we are changing the ratio of the ingredients of the mix. And every ratio change changes the resultant pH significantly. So how do you realize what you wind up with? With this. That's it. You think I'll repeat something like this on the next exam? You're damn right. It'll be there. I already have enough information to know this. So you're forewarned right now. I'm telling you what to expect. And as we head to chapter 19, and here's a reminder about chapter 19, as I've already reminded you, you will see that just about all the important chemistry from chapter 19 depends on, guess what? Bronsted-Lowry acid-base chemistry. That's why we do this stuff first, because it lays foundation for getting into chapter 19 stuff on equilibria, which involves salts of limited solubility in water. Because just about all such salts have a basic anion, an anion component, which is a stronger base than water. Which means the solubility of any such salt is drastically affected by pH. So back to Bronsted-Lowry acid-base chemistry. Then when we get further along in chapter 19 and carry this on into chapter 22 on electrochemistry and start looking at the possibility of forming a whole slew of different complex ions, like ammonia complex ions, like hydroxyl complex ions, all of which have a stability dependent upon pH. Because for an ammonia complex ion, you've got to have a basic system. Otherwise you murder ammonia and you kill the complex ion. Hydroxyl complex ion, got to have a basic system. Otherwise you murder hydroxide ion and kill the complex ion of hydroxide ion. All this stuff depends on pH. That's why we make such a big deal of chapter 18. And chapter 18 is with us from now till the end of the pipeline. So, you got to get to chapter 18 stuff. And you will have ample opportunity to do that if as yet you have not done that. But get at it now, please. So we carry on with this stuff. Sulfuric acid solution we talked about last time. Let's wrap up our considerations. To repeat, there are three subcategories of polyprotic Bronsted acids. And calculation of hydronium ion for each is different. Requires a different analytic perspective. Sulfuric acid solution. The parent acid is the sulfuric acid molecule, which is a strong acid. But the parent acid is molecular. So we know the first ionization reaction is not an equilibrium reaction. It goes 100%. As we recognized last time, that guarantees that the value for the hydronium ion concentration for any water solution of sulfuric acid cannot be smaller than m sub I. It's got to be at least equal to the numerical label on the bottle. If it's 1.0 molar sulfuric acid solution, hydronium ion concentration is at least 1.0 molar. Now we pay attention to the second reaction, which occurs when sulfuric acid solution is prepared, which can also contribute to the solution hydronium ion concentration, which is the ionization of hydrogen sulfate ion, which is subject to equilibrium control. So the extent is 0 to 100%. And the 0 to 100% depends on KaHSO4 minus, which is a big number as far as Ka for weak acids go. 1.2 times 10 to minus 2. So you can get this stuff to easily ionize 100% by dilution. And 1 over m sub I. The more dilute solution, the greater this reaction proceeds left to right before this condition is established. So from this we recognize, as we wrote last time, for any water solution of sulfuric acid, the hydronium ion concentration is m sub I, the label on the bottle, plus the sulfate ion molarity. Because all that's doing is summing up the contributions made to the hydronium ion concentration for the solution from the first reaction, m sub I, and the second reaction. from which it also follows that M sub I is the sum of the molarities for hydrogen sulfate ion and sulfate ion. And with these two relationships, you can immediately get at the hydronium ion concentration or any other solution property for sulfuric acid solution, which depends on pH in short order fashion. So we'll ask two remaining questions before we proceed. As a function of M sub I, how does the hydronium ion concentration compare to the sulfate ion concentration in H2SO4 solution? Well, let's look at boundary conditions. M sub I is V large versus M sub I is V small. M sub I is V large. Let's ask one more question. If M sub I is very large, do we correspondingly expect a very large value for the hydronium ion concentration? Hell yes! It's M sub I at least. Now, if M sub I is very large, to what kind of extent does this reaction proceed left to right prior to establishment of equilibrium? Large extent or small extent? Small extent. So how will the hydronium ion concentration for a sulfuric acid solution in which M sub I is very large, how will the hydronium ion concentration compare to the sulfate ion concentration? Let's imagine it's 6 molar sulfuric acid solution. In 6 molar sulfuric acid solution, you'll find out this second reaction is going to a very small extent. It's just a couple of percent. So how does the hydronium ion concentration compare to the sulfate ion concentration? It's a hell of a lot larger, isn't it? Now, what if M sub I is very small? Now, if M sub I is very small, the second ionization reaction is going to about 100%, if not 100%. That means the hydronium ion concentration compares how to the sulfate ion concentration? Not equal.
It's going to be 2 races.
About? Impossible. Hydronium ion concentration, sulfate ion concentration can never be the same for sulfuric acid solution. If I make the statement that a student comes along and has reported that he or she has prepared a sulfuric acid solution in which the hydronium ion molarity is 1.5 times the sulfate ion molarity. 1.5 times. Do you accept that statement? I've asked this on exams before. I'll start with a hint. You sure as hell better reject that statement because it's impossible. And we're now asking the question which underlies recognizing why that condition for concentrations of hydronium ion and sulfate ion respectively is not possible. M sub I very large, hydronium ion molarity is huge next to the sulfate ion molarity. We've just been through that. But if M sub I is very small, then the second reaction is also going practically 100%. Which means you got hydronium ion from this and hydronium ion from this. So the hydronium ion molarity, when M sub I is very small, will be twice the sulfate ion molarity. Twice. And it cannot be smaller than twice. Never. Because this guarantees you've got a hydronium ion molarity which is equal to the label on the bottle. And if this goes 100%, then you've got a hydronium ion molarity which is twice the label on the bottle, and the sulfate ion molarity is the label on the bottle. But 2 to 1, less than that is impossible.
Unless M sub I is large.
We already talked about the M sub I large.
If M sub I is large.
If M sub I is large, then the hydronium ion molarity is huge next to the sulfate ion molarity.
I thought you said they're top. I know. If so it's even larger than 2 to 1.
Larger than 2 to 1. Look, let's imagine this is 6 molar sulfuric acid solution, okay? That means hydronium ion concentration is at least 6. And in 6 molar sulfuric acid solution, I don't really remember right off the bat what the extent of this reaction is. I'd have to calculate it. But if it's 10%, then the sulfate ion molarity would be 0.6. And the hydronium ion molarity would be 6.6. And 6.6 is 10 times bigger than 0.6. Okay? Now, let's try one. I will stipulate that we got a sulfuric acid solution in which we are told that the hydronium ion molarity is 4 times the sulfate ion molarity. What for this solution is the hydronium ion molarity? What's M sub I? What's the hydrogen sulfate ion molarity? How do you get it? If you're not going to tell me, I'm not going to tell you. What you need is on the board. Hydronium ion is 4 sulfate ions. Okay? Now let me show you something else if you haven't yet realized it. If I take this relationship and put it together with this relationship, what do I get? More to the point, if M sub I is equal to the sum of those molarities, what if I put the sum in here and replace M sub I with hydrogen sulfate ion plus sulfate ion? Do I also get this? But get this. I know what's going on here. You're all used to looking at X's and Y's. Well, the hell with X's and Y's. We're now dealing with real stuff. I see students working these problems and they'll say, let me let X equal the hydronium ion concentration. What the hell for? You're just making more puzzlement for yourself. If you're looking for the hydronium ion concentration, write it as such. Don't say let X equal this and then start monkeying around with X's and Y's. It's pretty soon you forget what the hell X is and Y and Z and Q and all that junk. Don't do that. Don't make your life more difficult. Learn. That's what we want to do. I'm trying to wean you away from that crutch stuff. Like students continue to ask me, and they always will, why don't I use ICE tables for equilibrium analysis? We are. I just don't call it that. Because I don't want you to think in terms of give me a crutch and let me rely on this crutch. Give me a recipe and let me shove everything into the recipe and don't think. Once you don't think, you lose. Game over. But you know this. You've heard this sermon time and again, and you're going to hear it until the end of the pipeline. Because the only way to give you the opportunity to succeed is to think. And once you turn off thinking, then you are inviting disastrous loss. I don't want that. Because you're never going to get at chemistry or any form of science or anything which requires thinking once you turn off the thinking process. How can you? You want to walk across the street with no legs? Go ahead, try it. You can't do that. Well, what do you want to do here? I mean, if you want to calculate a concentration, do you realize that if you wish to calculate a hydronium ion concentration or any concentration value for a system component of sulfuric acid solution, you have to use this? You have to use this. I mean, unless I give you a sulfuric acid solution molarity and I say the second ionization reaction goes 50%. Now you don't have to do any calculation. Because once you got M sub I, if the second reaction goes 50%, then hydronium ion concentration is 1.5 M sub I. But if you don't know the ionization extent for this, if you don't know the percent extent, then you got to use this. Well, tell me, with what we have here, with this given, can we make substitutions for each term in here except one? Because then you got one equation, one unknown? Enough said, do it. You know what to do now. We go to the next problem. Do it. And if you have trouble, see us. But we've told you what to do. The rest is arithmetic. Now then, the parent polyprotic acid is also molecular, so in that respect like sulfuric acid, but it's weak. We will find out, provided you understand this, that calculation for solution properties like hydronium ion concentration, parent acid molecular and weak, is easy. Nothing to it. Nothing to it because you only have to pay attention to the first ionization equilibrium. Let's take a look at why. In the notes, you have a detailed discussion of the analysis of calculation of the hydronium ion concentration for hydrated CO2 solution. So I'm not going to repeat what's in the notes. Let's pick on H2S solution. If you've looked at our acid-base table, you see there's a fair number of weak molecular polyprotic acids. There's oxalic acid. You don't know it by name, but it's the first acid in the weak acid column. Condensed or compressed formula is H2C2O4. But it's HOOCCOOH. If I try to give you a formula that corresponds to structure. And phosphoric acid. H3PO4 condensed formula. H2S, H2CO3. And the conjugate base of phosphoric acid is a diprotic acid. That's H2PO4 minus. Those are all in the table. Here's the first ionization equilibrium reaction for H2S, which by definition is Ka1 for H2S. The value is 1.1 times 10 to minus 7. I pulled it off the table. Here's the second ionization reaction. HS minus plus water. Double arrows, hydronium ion, and eek, sulfide ion, AQ. K is by definition KaHS minus, which is Ka2 for H2S. Because after H2S ionizes once, you get this. So HS minus ionization corresponds to the second ionization of H2S. Thus the label Ka2. The value I know has got to be less than 1.8 times 10 to minus 60 for this K value. How do I know that?
Well, for one, we know it has to be really small because the products are extremely small and acid to bases.
Well, you can say something more definitive than that. You see this stuff in the table? What do you know about this stuff?
Sulfide ion is a very strong base.
How strong is it?
It's like the strongest. Not quite the strongest.
Say something more. It's a stronger base than what?
Hydroxide.
Stronger base than hydroxide ion. What's that mean?
Its Kb is greater than that of hydroxide.
Yeah.
K is the conjugate acid has to be weaker than that of water.
That's right. That's it. You got it. Once I realized that this is a base stronger than hydroxide ion, which the table information tells you, then I am at the same time realizing from the KW equals KA times KB relationship that whatever KA is for this thing, it's got to be smaller than KA for water. And that's KA for water. That's what you got to do. Then you're understanding this stuff from a chemistry perspective. All right? Upshot. If K for this reaction is less than 1.8 times 10 to minus 16, then K for this reaction is a number which is damn tiny compared to this number. Now this is not a big number, but this number is huge next to this number. What's that mean? That means if I'm going to calculate the hydronium ion concentration for any solution of a weak polyprotic acid, which is molecular, I only have to pay attention to the first ionization equilibrium. Because for any such acid, Ka2 will be a whole lot smaller than Ka1. You can do the numbers analysis if you want. Pick any concentration you want for any weak molecular polyprotic acid. And sit down with scratch paper and prove to yourself. You don't need to go beyond the first ionization equilibrium to calculate correctly the hydronium ion concentration for the solution. Now, is this surprising? Is it surprising that Ka2 for a weak molecular polyprotic acid has got to be a whole lot smaller than Ka1? Is that surprising? Well, if it's not surprising, Professor Coulomb, tell me why it's not surprising. Did you all learn about Professor Coulomb and his considerations in 2045? I sure as hell hope so. Because in my humble way, which you know is any damn thing but humble, I tell my 2045 students, the most fundamentally important law of all of chemistry is Coulomb's law. What does Coulomb's law tell us?
That charges are either attractive or repulsive to other bodies.
What kind of charges are attractive?
Electrical.
What kind of electrical charges? There are no other kind of charges except electrical.
Positive, negative.
Opposite. Fair enough? Positive, negative charges. Like protons attracting electrons, which maintains the composition of any atom. You learned about atoms in 2045, didn't you? Okay. Now then, it's not just charge that we have to pay attention to, but charge density. You think the charge density of a proton is, even though it's only +1, do you think the charge density of a proton is extreme? Charge density. Yes. It's only +1. Why is that charge density extreme? This proton, you know how big it is? For the hydrogen atom, the size of the proton, its nucleus, is less than 0.1% of the atom itself. The space defined by this mysterious critter called the electron, which is a particle in a wave. It's waving while it particulates. Okay. Defines the atomic volume. Any atomic volume is defined by essentially massless particles. Ain't that interesting? And these atoms are pretty hard. They are somewhat squishy, which provides the origin of London forces. You did that in 2045, didn't you? Goody. But any atom which has a volume a whole lot bigger than its nucleus has the volume defined by massless particles, electrons. Because if you take any atom there is and add up the total mass of all of its electrons, it won't come close to the mass of one of its protons or neutrons. Isn't that interesting? These electrons are really interesting, mysterious critters. You did that in 2045, didn't you? So Coulomb's law tells us that particles with appreciable positive and negative charge densities respectively attract each other quite strongly. And if they have appreciable positive charge densities only, all the particles involved are plus, or all the particles involved are minus, then the repulsion effect between and among these particles is extreme. And look what you got here. Because to make this reaction go, you have to take away H plus from this thing. Now you realize why this is such a damn strong base? This has got a high negative charge density. It's a monatomic species and it's got a charge of -2. And from this thing you're trying to take away H plus, which has got a significant positive charge density. The attraction between H plus and sulfide ion, which maintains the integrity of this thing, is extreme. You got to fight that to get H plus away from this thing. Well, that's not easy to do. That's why when you're taking away H plus from any anion, which has got a substantial appreciable negative charge density, you're looking at a Ka value which is guaranteed to be damn tiny. Even more so for taking H plus from oxide ion. I mean from hydroxide ion to make oxide ion. Because oxide ion is smaller than this. They're both 2 minus. The negative charge density of oxide ion exceeds this. Because oxide ion is smaller than this. That's why on our acid-base table you see oxide ion to be a stronger base even than this thing. We're going to talk about this kind of stuff in detail in chapter 23. So those are some, shall we say, seed comments. Maybe when we get to chapter 23 you say, I remember him saying something about that before. All right? So if we don't have to pay attention to the second ionization equilibrium to calculate hydronium ion concentration, then this applies to this. Because the second ionization isn't contributing measurably to the hydronium ion concentration. So this applies, and I cross-multiply. Molarity is m sub I value 0.10. So 0.10 times this, take the square root, there's my hydronium ion concentration. Now let's have more fun. On the acid-base table, you'll see that the hydrogen sulfide ion has a reported Ka value on the order of 1 times 10 to minus 19, with an approximation sign in front of that value. You recognize that determining a value like this reliably is awfully damn tough. You know what kind of concentrations you're measuring to get a Ka value like this? Are very small. And measuring these concentrations reliably is damn difficult. Like if we threw one acetic acid molecule in a university swimming pool full of deionized water. We know it's there, but I defy you to find it. It's hard. And these are the kind of things which research chemists often encounter. Body chemistry. Some poisons, for example, to the human system are notoriously toxic at very, very tiny concentrations. But you got to get in there and find these damn things if you're going to figure out how to combat this poison and the effect it exerts on the human system. All right? Well, we'll take this estimated value and write the equilibrium constant expression for Ka2. There it is. Now what have we found from Ka1? And what have we found from the fact that Ka1 is huge next to Ka2? Notice that with Ka1 being 1.1 times 10 to minus 7, if we take 1 times 10 to minus 19 as the value for Ka2, Ka1 is 1 trillion times bigger than Ka2. 1 trillion times bigger. Whoop-de-doo. That's more than all the people on planet Earth. We have found from the determination of the hydronium ion concentration for our H2S solution that these two concentration values compare how? You see the legitimacy of x squared over m sub I minus x? So these two concentration values compare how? They're equal. And there's the sulfide ion concentration. It's Ka2. Statement. For any polyprotic weak molecular acid. Polyprotic weak molecular acid. The species which is produced by the parent acid losing H plus twice, like sulfide ion from H2S. You want to call it the double conjugate base of the parent acid? Always has a value which is equal to Ka2. Because after Ka1, the remaining equilibria aren't going anyplace. So with that, let's ask a couple more questions of a related nature. If I tell you that Ka true carbonic is 2.5 times 10 to the minus 4, it's in the notes. And as you know from the information in our acid-base table, Ka for hydrated CO2 is 4.2 times 10 to the minus 7. And for the most part, this is what you get when you bubble CO2 in the water instead of that. But if I had a solution in which true carbonic acid was the solute in one of the solutions and hydrated CO2 was the solute in the other solution and the molarities were the same, true carbonic 100th molar, hydrated CO2 100th molar, which solution is more acidic? True carbonic, you're damn right. A good deal more acidic. Now, which solution has the higher carbonate ion concentration? Think before you ask. Answer, pardon me, not ask. How do carbonate ion concentration compare for these two solutions?
I said true is much greater.
Wrong. Is carbonate ion produced by double proton loss by the parent acid regardless of what the parent acid is? Yes, it is. If I take away two H pluses from this, I get this. If I take away two H pluses from this, I get this. Call it the double conjugate base of either of these acids. So tell me, the carbonate ion molarity is the same for these solutions. Isn't that nice? That's what we talked about up there. Tell me the value. Tell me the value for the carbonate ion molarity in any solution of true carbonic acid or hydrated CO2, provided that these are the only solutes in the respective solutions. Correct. There's the carbonate ion molarity, because that's Ka for bicarb ion. And bicarb ion is the species which is derived after either of these acids loses H+.
What is the difference, what is the significant difference between what you call true carbonic acid and what you call...
We'll talk about that in chapter 23. It's a structure question. Okay? And now, take a look at question 1854. We're looking at a water solution of phosphoric acid, a triprotic, weak molecular Bronsted acid. The formula which corresponds to its structure is this. The compressed or condensed formula is this. But you know, if I give you this formula and you start writing a Lewis structure and start gluing hydrogen to phosphorus, all wrong. So I don't want to do that. I'd rather use this formula. Consider such a solution. 6.0 molar. All right? Here's what you want to get. The necessary data are supplied, not only in the statement of the question, but they are now contained in our information sheet. You know, the sheet I give you for each quiz and exam. Question number 1. How do you calculate the hydronium ion concentration for this solution? Or more to the point, you see here given 3 K values, Ka1, Ka2, Ka3. How do you get the hydronium ion concentration? You use Ka1 and that's all. So that solves that part of the puzzle. How do you get HPO4 2 minus concentration? Better yet, tell me the value. Tell me the value.
6.3 times 10 to the negative 8.
6.3 times 10 to the minus 8 is a winner. There it is. That's Ka2. So then finally, how do you get the phosphate ion molarity? Because here's the phosphate ion molarity expression. You're going to have to go to Ka3, because Ka3 corresponds to the equilibrium which generates phosphate ion. Oops. In your mind's eye, Ka3 corresponds to the equilibrium reaction established by this reacting as an acid with water, this plus water, double arrows, products, hydronium ion and phosphate ion. You want to get phosphate ion. You got the hydronium ion molarity from Ka1, didn't you? So you know this part. And HPO4 2 minus molarity is 6.3 times 10 to minus 8, so you know that part. Oh, you got 1 equation, 1 unknown. Big deal. Nothing to it. Now then, next time, we talk about getting the pH for a solution like 100th molar ferric nitrate. I advise you strongly to read through this before we discuss it. This one's real fun. And here comes charge balance.